Hey everyone, welcome to this video about finding the inverse of functions. So we're going to be working with things where, basically like this, finding inverses kind of like this. So I'll give you one thing and then you'll find the other. If you've never used my videos before, you're going to want to pause and try the examples when prompted. And there are always free guided notes available at divideandconquermath.com. And hey, while you're here, maybe you consider liking my video or subscribing to my channel. That super helps me out. Okay, so let's do a quick review. So before we begin this, you just need to know what a one-to-one function is. So hopefully if you know what that is, you can just look at this right away and know. If you aren't familiar with that, you might want to just watch my other video on that, which I will drop a link to that in the description of this video. So this function is, this is a function for sure, because it passes the vertical line test, but it is not one-to-one because it does not pass the horizontal line test. So not, I'm just going to write one-to-one, that'll mean one-to-one. But this other one, it definitely passes the vertical line test for sure. And then we can see here it also passes the horizontal line test, so this would be one-to-one. So like I said, that's something that you should just kind of know what those functions are. It'll just help you with this particular lesson. And so now we can talk about what is the inverse of a function. So the reason why I even had to bring up this one-to-oneness is that functions that are one-to-one like this, they have what's known as inverses. And what is the inverse? So the inverse of a function is found by really reversing the order of its coordinates to from xy to yx. And it's denoted like this. So it's got like this f to the -1 or y to the -1. So notice that this is special notation. This is not an exponent in the way that we would normally think of an exponent, where you'd like flip it upside down and then evaluate. In this context, this is what indicates that you are working with an inverse. So it's two things that could mean the same thing just depending on the context. Okay, so the basic idea behind this, it's just the idea of flipping the x and y coordinates. So just to check your understanding here, maybe you want to pause for a second, you should be able to find the inverse of this function here. Hit play when you're ready. So the inverse in this case, like I said, it's just the idea of flipping your x and y coordinates. So if I just have a set of points, this is all that I would have to do. I would literally just flip the x and the y, and that's it. Now, most of the time it's not going to be this simple, of course, and so now what we're going to talk about in this video is just how do you find the inverse. So I've got outlined steps here. Highly recommend that you write them all down. They're very simple. So first of all, it works best if you have your f of x in terms of y. So remember, a lot of times f of x and y, they can be interchangeable. This is actually one of those cases where it's better to actually just replace the f of x with the y. Then the next thing that you want to do is then interchange where your x's and your y's are, so flip-flop their spots. Then from there you'll solve for y, and then finally you'll replace y with the inverse notation because you have found the inverse. So this is kind of a trick to help you get there. Okay, so using these 4 steps, I'm actually going to label the next problem with these 4 steps just so you can kind of see how this all works out. And if you need to pause the video to write everything down, go for it. Okay, so what we're going to do is I'm going to give you a function. It will be a one-to-one function, and we will find its inverse. So starting with the first step, I just want to rewrite this function with y instead of f of x. Like I said, it just makes it a little bit easier from a psychological standpoint to deal with. That's really it. Just makes it nicer to work with. Okay, so the next thing that you want to do is wherever you had a y, you now want to replace it with an x and vice versa. So all I'm doing is rewriting the problem but interchanging the x and the y. Okay, so now what you want to do is you want to solve this problem for y. So to do that, first I want to subtract off the 1, so I'll rewrite this. This becomes 3y equals x minus 1. And then I will divide each parts by 3, oops, like this. So I get y equals 1/3 x minus 1/3. And now that I have solved this, I can actually go ahead and just restate this with the inverse notation. Now, if you started with y, then you'd want to write a y inverse here. But since we started with f of x, we're going to switch it back to the f of x notation as shown. Okay, so that's the first thing that I wanted to do. But now the other thing that I want to do is I also want to graph this. So starting off with this f of x equals 3x plus 1, notice this is in y equals mx plus b form. So here my y-intercept would be 1. So first let's plot this. Mark my 1, and then I go up 3 and over 1 with the slope. 1, 2, 3 over 1. Up 1, 2, 3 over 1. Okay, so now that I've got this kind of sketched out, here's my f of x function. So now what I want to do is I just want to draw the inverse. So let me write that down. So this was 1/3 x minus 1/3. So this will be a little bit difficult to approximate, but I'll do my best. So this is still in that y equals mx plus b form. My y-intercept is negative 1/3. So let's see, I'll come down to here, and then I'll just go up 1 and over 1, 2, 3. Let's see if I can do that again. And let's see if this does what I need it to do. So let's see, I think I'm just going to use the 2 points and see if maybe that will work. So yes, this will indeed work. So here's my inverse. Okay, so just kind of notice, look at the graph that you have. We want to make a deeper observation a little bit. So just kind of look at where we're at and keep this in mind. We'll flip back to it in a few minutes. Okay, so now what I want to do, I actually want to have you try this one. So pause the video, determine this one, and then hit play when you're ready to see the solution, and also graph this g of x with its inverse. Okay, so I'm going to start by following the same steps. So I take y equals negative 1/2 x plus 4, and then I flip-flop my x and my y. Now I have to solve for y. So I go ahead and I subtract the 4, so now I've got negative 1/2 y equals x minus 4. And then I will multiply everything times negative 2 so that I can get rid of that fraction. And so this will become y equals negative 2x plus 8, and then I just write this in its proper notation. So there we go. Okay, so now what I need to do, let's see, let me make sure I have enough tick marks. 1, 2, 3, 4, 5, 6, 7. Oh, I need one more. Let me just add that up here at the top. There, okay. So I want to first graph g of x equals negative 1/2 x plus 4. So once again, this is in that y equals mx plus b form, so I'm going to come up to 4. So 1, 2, 3, 4. Then I'll go down 1 and over 2. And let's see, that'll be good enough to determine the line. So I'll just go ahead and graph that as shown. So there's my g of x. And now I want to compare that to, oops, I wrote this as f prime of x. This should, I wrote this as f inverse. This should really be g inverse. Okay, so I relabeled this. So now let me graph this. So I'm going to come up to 8 as my y-intercept. So 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to go down 2 over 1. And this we might have problems with, but we will figure it out. So let's see. And g inverse of x. So let's see, I'll label this one. I'll label it down here. G inverse of x. Okay, so I've got my two functions, although this isn't quite as easy to see as I had hoped it might be. So you know what? I'm actually going to do something a little different. I'm actually going to use some graphing software to make my point. So I'm going to go to desmos.com just to show you guys kind of a deeper point with this. So let's go. Okay, so here we are at this website, desmos.com. Super great graphing software if you're ever trying just to graph really anything. It's all free, so I use it all the time actually. So what I've drawn here, this red line, so this is that 3x plus 1 that we were just looking at in the very first example. So you might want to just have this kind of in front of you. And now what I want to do is I actually want to show you a perfect visualization of its inverse. So this was the first inverse that we saw. So take a look at how the two inverses are kind of lined up to one another and just keep a mental image of that, okay? So what I'm going to do is I'm actually going to get rid of both of these for a moment. And now I want to look at the second example that we were just looking at. So this first line, this was my g of x, that negative 1/2 x plus 4. And now I want to take a look at its inverse. So once again, take a look at this. Okay, so what I'm trying to point out here is that if you look at this, there's actually like a reflection here, but it's not the type of reflection, it's not like over the x-axis or the y-axis. Where this reflection actually happens is over this black line. This black line is y equals x, so it is actually an equation, and this is the relationship between all inverses, or all functions and their inverses if they have an inverse. It's always going to work like this. So notice that if I were to reflect this solid purple line over this, I would indeed get to this dotted line. And if I go back to the very first function that we were looking at, you can totally see how these two are reflections of one another. So that's actually kind of the visual relationship between functions and their graphs. So coming back to this, what is the relationship that a function has with its inverse on a graph? The inverse is a reflection of the function over this line y equals x. So there is still this like visual connection. Okay, so now I just want to do two more examples with you of just not lines, but you don't have to graph them this time, just to kind of give you a little more experience with finding inverses. So pause the video here and hit play when you're ready to see the solution. So starting with the first one, so I'm going to do the same set of steps before. So I'm going to first replace this y equals the cube root of x, and then I'll flip my x and my y like this. Now, to get y by itself, how are you actually going to do that? Well, this is a cube root. So to get rid of a cube root, you will cube both sides. And so that will give me y equals x cubed, and so the inverse will be h inverse of x equals x to the third. So those two things are inverses. Okay, so now let's take a look at this other one. Now notice that this has been stated a little bit peculiar. You know what I'm trying to say, right? So this has been stated in a specific way. So let's go ahead and find the inverse of this one. So I've got y equals x squared. I will flip my x and my y. And now to solve for y, so I'm actually going to take the square root. But here's the issue. If you think back to the square root property, normally what you would have to do is you would have to take plus or minus this side. But this is actually, because we have this condition here, we don't actually have to worry about this. So my answer here will be y equals the square root of x, and x has to be greater than or equal to 0. Now, think about what this actually means. I think it's actually helpful to have a visual here, so I can just do a very quick sketch of this. So this is a parabola. My first function is just a parabola, right? So this would be my x squared, but I only want the half of it, the positive half. That is this function. And so then when I find the inverse, so that inverse is going to look like this. And so if you think about what the domain of just the square root of x is, x always has to be greater than 0. So if I didn't restrict the domain on this x squared, I wouldn't actually be able to find the inverse of this. Because if I actually extend the parabola like this, this function, as we know, is not one-to-one. So that's why we have to make those restrictions, and then that's why this example works. Okay, so I have just one other topic I want to cover with you guys. So we're going to talk about using composition to determine if two functions are inverses of one another. So here's the way that works. To perform composition, basically you're going to take f composed with g and g composed with x. And if when you do that composition that equals x, then that means that the two functions are indeed inverses of one another. So just in case you're a little rusty on how composition works, I will go through it with you in this first example. So what we want to do here is we want to determine if the functions are inverses of one another, and we want to do this by using composition. So let's start. I will first show you this side. So f composed with g. So what this actually means is that you're going to take f of g of x, and where you want to start from the inside and work your way out. So I'm going to replace g of x with the function itself, so this function. So this is going to equal f of 1/2 x plus 3. So now what I want to do is I want to take this function and I want to actually just replace it into the x part of the f of x function. So this is going to replace this part of this function, because that's what function notation means. So if I make just that replacement, this becomes 2 times 1/2 x plus 3 minus 6. So now what I have to do is I have to work this out all the way. So as I distribute this, 2 times 1/2 x is going to be x. 2 times 3 is 6, and then subtract the 6. And hey, look at that. We got just plain old x. So that's what this property is talking about. You want to see if you get just plain old x. All right. So make sure you have this written down if you need it. I'm going to clear it off. And so now what we're going to do is we're just going to go the other way. So you should be able to do this both ways. So I'm going to take now g composed with f. So now I'm going to take g of f of x. And so what I would recommend is that you pause the video and try to finish this one on your own. Just do the whole composition and then hit play when you're ready. So this becomes, so we're starting from the inside out. So I need to take g of 2x minus 6, and now I need to plug 2x minus 6 this into the x spot of the g function. So this will be 1/2 times 2x minus 6 plus 3. And now I distribute. So this is 1/2 times 2x, so this is x. 1/2 of 6 is 3, and then plus 3, so ultimately, hey, this still equals x, so yes, they are inverses. Okay, so that's kind of the idea behind this. And if it doesn't work in one direction, then you don't have to go any farther. So what I want you to do now is I want you to try that test with this function. Go ahead and test it out, hit play when you're ready. Okay, so I'm going to go ahead and do this. So I'll take f of g of x. So let's see. That's f of g of x, and I'll start from the inside and work my way out. So this is 1/3 x plus 6. And now I want to plug that into my x function. So this becomes 3 times 1/3 x plus 6, and then the plus 1 at the end. So remember, I am just replacing all of this right in the x part. The rest of the function stays intact. So now if I distribute, this becomes x plus 18 plus 1. So this equals x plus 19. So right here, we don't have to go any farther. This tells us right away that they're not inverses. So I can just note that and I'm done. So the only way this works is if you get just x. If it's not like that, then they're not inverses. And so that actually covers everything in this section. So hopefully that was helpful for you, and I'll see you guys next time.